In this video, we're going to start talking about matrices. Now, if m and n are positive integers, so say 1, 2, 3, 4, etc., okay, then an m by n matrix is a rectangular array of the following sort, in which each entry Aij of the matrix is just some numbers. So these are a bunch of numbers here. So I'd also like to note that here we have rows, okay? So this would be row 1, row 2, row 3, and then all the way down to row m. So rows are counted on this side, on the right side, and going across that way. We also have columns which go down this way. So this would be column 1, column 2, column 3, all the way out to column n. Namely, what we notice is that this matrix has m rows and n columns, where each of these Aij entries this Aij entry is in the ith row and the jth column. Namely, A32 is in the third row and the second column. So that's how these double subscripts work. All right. And again, I want to reiterate the fact that a matrix we always read a matrix as m by n, meaning that it's always rows by columns. So we always do rows first and then columns when we talk about an m by n matrix. A few other things to note. A matrix having m rows and n columns is said to be of dimension m by n. And so dimension for a matrix is kind of like its size. It's how big it is, right? If I said a 2 by 3, I would expect its dimension to be 2 by 3, which would mean that it would have 2 rows and 3 columns. And then another thing, when the number of rows and the number of columns are equal to each other, then the matrix is square of dimension m by m, or n by n, since we know that they're the same. Namely, some examples of a square matrices would be 0, 1, 2, 3, because that's a 2 by 2, or 3, 1, 7, 0, 2, 5, negative 1, root 2, 6. Okay, it doesn't matter what the numbers are. The important thing here is the size, okay, because this would be a 3 by 3. So these are both examples of square matrices because they have the same number of rows as columns. Now, also for a square matrix, so assuming we're in a square matrix, the entries A11, A22, A33, all the way up through AMM. So for instance, this entry, this entry, this entry, or this entry and this entry. As such, you can see that since they're on a diagonal there, what we really say, we call these the main diagonal entries. Namely, the main diagonal entries for a general m by m matrix would be these entries. Okay. Also, a matrix with only one row is called appropriately a row matrix. For example, something like 1, 2, 3, 4. Again, the numbers don't really matter. There are 4 columns, but only one row of that matrix. And similarly, a matrix with only one column is called a column matrix. So let's do some examples looking at the dimensions of the following matrices. This one has one row and one column. And thus, it's going to have dimension 1 by 1. 1. Okay. This one has one row, so it's again a row matrix. This would be both a row and a column matrix. This would be a row matrix, but it's not a column matrix because it has 4 columns. So it is so it has dimension 1 by 4. This one has 2 rows, 2 columns. So 2 rows, 2 columns. And so it would have dimension 2 by 2. And then finally, this last one has 3 rows, 1, 2, 3, and 2 columns. Thus, its dimension is 3 by 2. Namely, also note that this is a square matrix because the number of rows and columns is the same, so this would be a square matrix. And this one would not be square because different number of rows and columns. This one as well is not square because different number of rows and columns, but this one is because it has 2 of each. So this would also be square. Now it's time for you to try an example, so I want you to determine the dimension of the given matrix, and on the count of 3 I will reveal the solution. 1, 2, 3. So here we see that there are 1, 2 rows here, 1, 2 rows, but also 1, 2, 3 columns, and so it's going to be a 2 by 3 matrix. Most notably, also because the number of rows and columns are different, it will not be square. A natural question is now, you may be wondering, why is any of this really useful to consider? Well, one answer is that matrices help us solve systems of equations more easily by only focusing on the numbers involved. So we can kind of get away from, the idea of a matrix is that we can somehow get away from all the variables x, y, z, w, any other things that we might involve. Instead, we just focus on the numbers, which I think helps clarify things. I found students typically like matrices because of that, more than they like solving systems. So we need a bit more terminology thus to do this. Matrix derived from a system of linear equations, each written in standard form with the constant term on the right. We'll go through an example in a moment to see what that means. Is the augmented matrix of the system. Moreover, the matrix derived from the coefficients of the system, not including the constant terms, is the coefficient matrix of the system. All right? As an example of this, consider the following system of equations. For this system, the augmented matrix, so what do we do to form the augmented matrix first before I show you? We form it by taking all the coefficients, including also the constant terms, okay? Because that's what it says here. Each written in standard form with the constant term on the right, which we have, is the augmented matrix of the system. And so we're going to create the augmented matrix by just taking those numbers. So we would have the following augmented matrix. Namely, it would be, we have a 1, then a -4, then a 3, and then a 5 there. We branch, we kind of represent the equality sign by putting dots there, vertical dots, sectioning that part off. And then we would have -1, 3, and -1, then -3. 2, we account for the 0 y there that way, and then -4, and then 6. Similarly, the coefficient matrix is easy. We just drop all the constant terms. Namely, we would have the following as the coefficient matrix. 1, -4, 3, -1, 3, -1, 2, 0, -4, which again is just this whole matrix, but we dropped all the constant terms. So let's do a more involved example now. Here we have, let's go ahead and write the augmented matrix for the following system of linear equations. Now the first thing is we need to put this in standard form. We have variables here. I'll write variables. In order, I'm going to write them as x, y, z, and w. So we need to write this out in the standard form so that it looks that way. Namely, and this kind of explains, when you saw before, this kind of tells us why we've been trying to line things up so carefully and leaving gaps and stuff in our equations, is because it makes it much easier to turn it into an augmented matrix. So there's 0, that's plus 3y. There's no z, so we're going to leave a gap there. Minus w equals 9. No x, but there's a minus 3, there's a minus y. plus a 4z plus a 2w, which is equal to -2. And then we have an x. We have no y, but there's a minus 5z minus a 6w equals 0. And then finally, there's 2 x's, a 4y, and a minus 3z, but no w, so we'll have that equal 4. And now, again, you realize why we've written it this way, because it makes it much easier to find the augmented matrix. We just read off the coefficients. 1, 3, 0, -1, 9. Here, 0, -1, 4, 2, -2, 1, 0, -5, -6, 0, 2, 4, -3, 0, 4. Also note that we can use the notation Rn to denote the rows of a matrix. Most notably, we have the rows R1, R2, R3, and R4. This will become very helpful this notation will be very helpful when we do row reduction and Gaussian elimination, when we do Gaussian elimination, because our rows, our R's, are going to take the place of what we had as equations before. But before we get to any of that in a future video, let's have you work an example. Go ahead and write out the augmented matrix for the following system of linear equations, and also determine what the dimension of the augmented matrix is. On the count of 3, I will reveal the solution. 1, 2, 3. So here, because this is already in standard form, we have x's, y's, z's, and then our constants already there, all in nice aligned in columns and such. We already have it in what I guess is a standard form, but we don't have to do what we did in the last example, right, first. And so we just read it off to get our augmented matrix, and then we count up the dimension, 3 rows, 4 columns, so 3 by 4. For more practice, in these concepts and starting off with matrices, be sure to see page 549 of the textbook and work problems or exercises 1 through 4 and 7 through 26. In our next video, we're going to start setting up for Gaussian elimination by looking at elementary row operations.